aluminium is so common in modern life that it almost disappears into the background. It is in aircraft, cars, window frames, drink cans, kitchen foil, phone bodies, power lines, packaging, and countless machine parts. Yet this familiar silver-colored metal has a strange story. It is incredibly abundant in the Earth's crust, but for most of human history it was almost impossible to obtain as a pure metal. That combination makes aluminium unusual. It was not rare because nature lacked it. It was rare because chemistry locked it away. Once humans learned how to release it at industrial scale, aluminium went from a laboratory curiosity to one of the defining materials of the modern age. At its simplest, aluminium is a chemical element with the symbol Al and atomic number 13. In British and international scientific usage it is usually called aluminium, while in North American English it is commonly called aluminum. The difference in spelling does not change the element itself. It is a soft, non-magnetic, ductile metal, meaning it can be shaped, drawn, and formed without breaking easily. Its appearance is silvery and bright, and it reflects light very well. This is why aluminium often looks clean, modern, and almost mirror-like when freshly prepared, even though in real environments its surface is usually covered by a very thin invisible layer of oxide. One of aluminium's most important physical properties is its low density. It weighs only about 1/3 as much as steel for the same volume. That does not mean aluminium is always stronger than steel, or that it can replace steel in every structure. But it means that when engineers need to reduce weight, aluminium becomes extremely attractive. In transportation, weight matters constantly. A lighter aircraft needs less fuel. A lighter vehicle can be more efficient. A lighter component may be easier to move, assemble, or support. Aluminium's value is not just that it is a metal, it is that it offers metallic usefulness without the heavy mass associated with many traditional metals. The reason aluminium survives so well in everyday use is also the reason it is hard to find naturally as a pure metal. It loves oxygen. When aluminium is exposed to air, it reacts at the surface and forms a thin protective layer of aluminium oxide. This layer is not like rust on iron, which can flake away and expose more metal underneath. Aluminium oxide clings tightly to the surface and helps shield the metal below from further attack. This self-protecting behavior is one of aluminium's great advantages. It allows the metal to be used outdoors, in packaging, in construction, and in many environments where corrosion resistance matters. Chemically, aluminium sits in the boron group of the periodic table and is usually described as a post-transition metal. In compounds, it most commonly appears in the +3 oxidation state. That means aluminium tends to lose or share 3 electrons when it forms chemical bonds. The aluminium ion, Al3+, is small and strongly charged, which gives it powerful influence over nearby electrons. As a result, aluminium bonds often have a more covalent character than one might expect from a simple metal ion. This chemistry helps explain why aluminium forms stable minerals and oxides rather than existing freely in nature as shiny metal nuggets. Although pure aluminium metal is not found freely in nature, aluminium as an element is everywhere around us. In the Earth's crust, it is the third most abundant element after oxygen and silicon. It is not concentrated mainly in the mantle, and it does not usually appear in metallic form. Instead, it is locked inside rocks and minerals, especially as oxides and silicates. This is why the story of aluminium is really a story about extraction. Humanity did not need to discover a hidden supply of the element. The supply was already enormous. The challenge was finding a way to separate aluminium from the oxygen and other elements holding it in mineral form. The main industrial source of aluminium is bauxite, a sedimentary rock. Rich in aluminium minerals. Bauxite is not pure aluminium, and it does not look like the bright metal people recognize. It is usually earthy, reddish, brownish, or pale, depending on its composition and impurities. But inside it are compounds that can be processed to produce alumina, or aluminium oxide, which can then be transformed into aluminium metal. This chain from rock to oxide to metal is central to aluminium production. It also shows why aluminium's abundance alone was not enough. The element had to pass through a demanding industrial process before it could become useful metal. The discovery of aluminium as a distinct metal was announced in 1825 by Danish physicist Hans Christian Ørsted. At the time, isolating aluminium was a major scientific achievement because the element was so tightly bound in its compounds. Early aluminium was extremely difficult to produce and therefore expensive. It was not yet the everyday material of cans and aircraft. It was closer to a precious scientific novelty. This period is important because it reminds us that material value is often shaped by technology. A substance can be abundant in nature but rare in human hands if no practical process exists to obtain it efficiently. A major step toward practical production came in 1856, when French chemist Henri-Étienne Saint-Clair de Ville initiated the first industrial production of aluminium. His work made aluminium more available than before, but not yet cheap enough for the mass market. The true breakthrough arrived in 1886 with the Hall-Héroult process, developed independently by French engineer Paul Héroult and American engineer Charles Martin Hall. This process used electricity to separate aluminium from aluminium oxide. It transformed aluminium from a difficult specialty material into something that could be produced at scale. In many ways, modern aluminium begins with that industrial and electrical revolution. Once mass production became possible, aluminium's role expanded rapidly. Its low weight, workable nature, attractive appearance, and corrosion resistance gave it a place in many industries. In the 20th century it became increasingly important in transportation, engineering, construction, and packaging. By 1954, aluminium had surpassed copper to become the most produced non-ferrous metal. Non-ferrous simply means it is not based on iron. That milestone shows how quickly aluminium moved from rare curiosity to industrial giant. It was no longer just a metal for chemists and specialists. It became part of the infrastructure of modern economies. In transportation, aluminium's main advantage is the relationship between strength, formability, and weight. Aircraft are the classic example, because every kilogram matters in flight. But the same logic applies to cars, trains, ships, and many engineered components. Aluminium can also be alloyed with other elements to improve its performance for specific uses. Pure aluminium is relatively soft, but aluminium alloys can be much stronger and more suitable for demanding applications. This is one reason the metal became so important. Engineers are not limited to one fixed version of aluminium. They can adjust its properties through alloy design and processing. In construction and packaging, aluminium solves different problems. In buildings, it can provide durable frames, panels, and architectural elements that resist corrosion and keep weight manageable. In packaging, it can be rolled into thin sheets or shaped into cans, creating light containers that protect contents and are easy to transport. Its reflectivity also makes it useful in insulation and lighting-related applications. These everyday uses may seem ordinary, but they reveal aluminium's deeper importance. It is not valuable because it performs one spectacular task. It is valuable because it performs many practical tasks well enough, cheaply enough, and at enormous scale. Aluminium also raises an interesting biological question. It is widespread in the environment, and aluminium salts are common, yet no living organism is known to metabolize aluminium salts in the way life depends on elements like carbon, oxygen, nitrogen, iron, or magnesium. Plants and animals generally tolerate aluminium, but it does not have a clearly established essential biological role. Scientists continue to study its interactions with living systems because its abundance makes the question worth asking. The story of aluminium therefore stretches from stars and isotopes to rocks, factories, aircraft, buildings, packaging, and biology. It is a quiet metal, but modern life would look very different without it. If you found this helpful, please like this video and subscribe for more explainers.